you ever paused to consider why the massive computing servers of Google never undergo a catastrophic system crash when handling billions of voice requests simultaneously? Back in the historical window of 2013, Google's engineering core confronted a terrifying reality that completely stripped their top architects of sleep. The computational telemetry revealed that every single Android user utilized voice search features for just 3 minutes a day. The absolute infrastructure load would incinerate their data centers. Resolving this meant instantly doubling their global server footprint, a trajectory that was financially and practically impossible. And from this precise crisis, a classified project was engineered that permanently shifted the trajectory of AI. The Google Tensor Processing Unit. To accurately process this hardware evolution, we must analyze the structural baseline of modern processor design. A standard CPU or central processing unit functions like a versatile general-purpose chef capable of executing varied tasks sequentially but heavily constrained by single-threaded execution loops. Conversely, a GPU or graphics processing unit operates as a massive parallel execution engine optimized to perform thousands of identical low-level mathematical steps simultaneously. While early machine learning models scaled entirely on top of GPU infrastructures, the exponential growth of deep neural networks quickly hit a wall where standard hardware nodes proved structurally inefficient and economically unsustainable. A Moore's law plateaued when Google scaled natural language speech recognition across mobile devices. The internal telemetries confirmed that third-party processing nodes could not support the continuous macro load. Management executed a strategic pivot to design an in-house custom ASIC, an application-specific integrated circuit engineered strictly for executing neural network calculations. If a CPU represents a highly versatile Swiss Army knife, a TPU functions as an unyielding ninja sword designed for a single operational directive, matrix multiplication. To compress a standard 4-year hardware design cycle into an absolute sprint, Google onboarded Silicon Valley engineering legend Neumann Jouppi, who bypassed traditional development loops to deploy operational TPU silicon inside live data centers within a record 15 months. At the core of this processing architecture lies the concept of a tensor, which represents multi-dimensional mathematical data arrays processed by deep learning nodes. Traditional silicon designs suffer from the notorious von Neumann bottleneck, where a processor expends vast clock cycles and power simply moving data back and forth between the memory banks and the execution core. To eliminate this high friction bottleneck, Google implemented a brilliant spatial design known as a systolic array, a term directly adopted from the biological pumping action of the human heart. Data streams continuously flow through a multi-tiered grid of interconnected processing cells, performing automated multiply accumulate operations in a single directional wave without needing to write intermediate results back to memory. To maximize operational throughput, the architecture leverages quantization techniques, converting complex floating point numbers into lightweight 8-bit integer frameworks. While this adjustment minimally impacts numerical precision, it drops the computational overhead significantly, multiplying overall execution velocity exponentially. The hardware contains a massive matrix multiply unit alongside a 24 megabyte unified buffer memory cell that eliminates external latency loops. Crucially, raw silicon remains inert without software integration, which is why Google deployed its software framework, TensorFlow, alongside the XLA or Accelerated Linear Algebra compiler to seamlessly translate high-level code directly into high-velocity machine instructions. While the Generation 1 TPU was strictly built for inference workflows, the introduction of TPU V2 and V3 brought massive training capabilities to the architecture. These advanced units generated such extreme thermal output that legacy fan systems failed, requiring the integration of custom liquid cooling pipelines running directly over the silicon. Today, modern infrastructure arrays leverage monster nodes like TPU V4 and V5P, which communicate via optical circuit switches using laser arrays rather than standard copper pathways, laid out in a three-dimensional torus topology to prevent data routing congestion. When thousands of these processors are linked into unified supercomputing clusters called TPU Pods, they form the absolute foundational engine where frontier AI models like Gemini undergo continuous training cycles. This leaves the entire tech landscape facing an intense civilization question. Who will ultimately dominate the global infrastructure layer of the artificial intelligence revolution? Will it be NVIDIA highly versatile, globally distributed GPU ecosystem, or will Google's highly optimized sovereign internal TPU matrix capture absolute algorithmic supremacy? Drop your insights and perspectives in the comments section below. Smash that like button, subscribe to the channel, and lock in all notifications to stay connected with high velocity tech analytics. See you in the next deep dive breakdown. Keep exploring. Join the frontier of AI revolution.